Hello everyone, my name is Grace. I'm a PhD student at Sorbonne Université and INRIA Paris under the direction of Fabrice, Rouillier and Alban Quadrat. I will talk about the computation of the L-infinity norm of finite-dimensional linear systems. Here, we consider four real matrices that will define us our linear dynamical system. X is the state vector, Y is the output vector, and U is the control vector. And we assume that A is stable, that is to say that all the eigenvalues of A are of negative real parts. Thus, the transfer function will be denoted by G of S as follows. So here we have the set of rational functions that are proper and stable, and the matrix consisting of these elements will be called the matrix valued function. Its L-infinity norm is the essential sup of sigma bar at I omega, where omega is in R. Here, sigma bar of M denotes the maximal singular value of this matrix M, which is the square root of the maximal eigenvalue of the Hermitian transpose of M multiplied by M. So now, about the importance of the L-infinity norm computation. In robust control, it is considered as a robustness measure, and in model order reduction, it is a tool for the error measurement. So now we start by explaining its properties. So when we have a positive value gamma, we define the matrix gamma squared I minus Hermitian transpose of G multiplied by G. Here, the Hermitian transpose of the matrix G is simply the transpose of G at minus S when S is equal to I omega. And the determinant of gamma squared minus G star multiplied by G is a rational function in S squared. Thus, when S is equal to I omega, this determinant is a rational function. It's written as N gamma omega over G gamma omega, where G omega, where N and G are co-prime. And moreover here, D does not vanish. Thus, for studying the roots of the determinant, it suffices to study the roots of the numerator polynomial. So hereafter, we consider only this polynomial N and we work on it. So for a matrix valued function that is of size U times V, okay, alpha will be considered as the maximal value between U and V, and the capital N is the maximal occurring degree of my polynomial of my matrix elements, and tau of G will be the maximal coefficients bitsize of the polynomial occurring in my matrix. So the degree of N with respect to gamma will be in the order alpha. The degree of N with respect to omega will be in the order of alpha squared by N, and the coefficients bitsize of N will be in the order of alpha squared multiplied by tau of G. And finally, the last property is that our curve of N is bounded on the gamma direction by the L-infinity norm. So now we can tackle our problem, and we start by the CISO case, which is the single input, single output. Here our transfer function is simply a rational function where its L-infinity norm is its maximal value of the module of G. And the module of G squared is a rational function in omega squared. Thus, for computing the L-infinity norm, we start first by computing the real roots of the numerator of the derivative function of the module of G squared. Then we take these values and we evaluate module of G over them, and we choose gamma bar to be the maximal one. And finally, the L-infinity norm of G will be the maximal value between this gamma bar and the module of G at infinity. As for the MIMO case, which means multiple input, multiple output, the problem of computing the L-infinity norm of G, which is a transfer function matrix, okay, it's the problem of computing the maximal gamma projection of the system of the critical points, okay, or the maximal real root of the leading coefficients of N with respect to omega. Here, N bar denotes the square free part of N, but hereafter we will consider that N is square free, and thus we will denote simply N bar by N, of course, without loss of generality. And here, the real roots of the leading coefficients of N with respect to omega are exactly the asymptotic values of the curve. So about the existing methods, most of them are numerical, such as bisection algorithms and eigenvalues computation over Hamiltonian matrices. Then in their paper, Cano and Smith developed a validated numerical algorithm for this L-infinity norm computation. And following their work, Chen, Maza, and Chi provided an equivalent study by using the theory of border polynomial, which transformed the problem of the L-infinity norm computation to the problem of studying the singular points or the system of singular points, okay? As for our propositions here, we propose three different symbolic numeric algorithms. The first one will be called the Ruhr method, the second one is the root separation method, and the third one is the Sturm-Abischt method. So we start first by explaining the Ruhr method by considering a zero-dimensional system, sigma, and we consider that the degree of n is less than g. So the first step of the Ruhr method consists of computing a linear separating form, which is t equal gamma plus a omega, and here a is of the best optimized size, which is in the order of log of g. Then a polynomial p is a univariate polynomial, which is the resultant polynomial of the shared system with respect to omega. And here the resultant polynomial with respect to omega is a univariate polynomial that embodies the gamma projection of my system solutions. The next step consists of computing a root decomposition, okay, in a way that we obtain a one-to-one correspondence between the real roots of the univariate polynomial p and the system's real solutions. And finally, it finds the isolating boxes of the solutions. So here we simply apply this method over our problem. We obtain the isolating boxes of the solutions, and we just pick the maximal gamma projection to be our L-infinity norm of T. Next, for the root separation method, here we start by computing the gamma projection of the system solutions to the gamma to the gamma axis, of course, by computing the real roots of the resultant polynomial of sigma with respect to omega. Here the blue dots consist of the real solutions of the system, and the blue crosses are the complex ones. Next, we compute the real values. Delta is the separating bound of the polynomial R gamma. M is the measure of the polynomial that embodies the omega projection of the system solutions. So S, which will be the slope of the linear shearing map, will be simply less than delta over m. But here S is of high size, which is in the order of D3 tau. So why we choose this high bit size of S? As we can see here, when we consider the red dots to be the real roots of my shared system, using this special separating bound, we can notice that the gamma projection of the shared system solutions is with the preserved order, which means that when a green dot is issued from a gamma I, it belongs to a unique interval gamma I minus delta, gamma I plus delta. So by this way and using this proposition, we can say that whenever we find or we locate the maximal green dot, okay, in an interval gamma I minus delta, gamma I plus delta, we consider that this gamma I is the searched value, that is the maximal gamma projection of my system's real solution. And in this case, the L-infinity norm of G is equal to gamma 3. Finally, the Sturm-Abischt method. In this method, we also start by projecting my system solutions to the gamma axis. However, here we don't need any separation. As we can see, gamma 3, which is the searched value, is the maximal gamma projection over which the GCD polynomial of n and its derivative with respect to omega admits at least one real root. So, theoretically speaking, we can simply apply the concept of Sturm-Abischt real root counting over this univariate polynomial, and we are done. Here we just recall that a Sturm-Abischt sequence is a signed subresultant sequence, which is similar to the remainder sequence, but with a controlled coefficients growth, and it's stable under specialization. Moreover, when we study the sign variation over the leading coefficients of this Sturm-Abie sequence, we obtain exactly the number of the real roots of our univariate polynomial. However, instead of computing a Sturm-Abie or subresultant sequence for this GCD polynomial and its derivative with respect to omega, which will be a little bit costly, okay, we apply this lemma that says that when P is a curve that is bounded on the x direction by x bar, the real roots of P over x bar are exactly the real roots of its GCD polynomial over x bar. And why we can apply this lemma to our L infinity problem? Okay, since we already proved that the polynomial n is bounded on the gamma direction by the L infinity norm of T. So we are in this situation, and here we can see that we want to choose the maximal gamma projection over which the polynomial n admits at least one real solution, and we do a sign evaluation over the values gamma I for counting the real roots. But instead of, or to avoid using a evaluation over some algebraic numbers, okay, we can simply choose a rational number between two consecutive maximal algebraic numbers, and whenever we find an intersection with n, or whenever we find over this rational value a real root, at least one, we can say that the maximal one is a real solution, and thus its gamma projection is the searched value, and in this case the L infinity norm of G is equal to gamma 2. As for the complexities of these three algorithms, for the real method, the complexity is the best known complexity, which is in the order of alpha 9 and 4 alpha plus tau. The root separation method is of very high complexity due to the large size of the separating bound of S. And here it is of complexity alpha 14 alpha and 5 tau of n. And the Sturm-Abie method, as we said, it consists either on the evaluation over algebraic numbers, which will give us a complexity of alpha 10 and 4 alpha plus tau of n, or over rational numbers, which will give us the complexity alpha 10 and 4 tau of n. Here we should mention that the Sturm-Abie method is adaptative, which means that it's different between the real method is that in the real method, whenever we apply this method, it will immediately compute us the whole system solutions. As for the Sturm-Abie method, it can, for example, whenever it starts to verify from the top of the gammas, if it finds this gamma that is verifies our conditions, it will immediately return it without having to pass through all the gamma projections, which will be explaining its behavior in the practical examples. We pass now to an example by proving in this proposition that the L infinity norm of the transfer function R, which is a transfer function depending on parameters, we proved it to be either one if xc, a parameter, is higher than square root of 2 over 2, or it is the maximal real root of this polynomial that we can see, which is a univariate polynomial in gamma having the following parameters, whenever c is less than square root of 2 over 2. So we choose one particular values for our parameters, and we compute the L infinity norm of R. First, by this proposition, we obtain this value. Then we apply our proposed method. Here the H1 is the Ruhr method, the H1 is the separation method, and the H1 is the Sturm-Abie method. And as we can see, the three of them return the same value as the value returned by the proposition. However, the function norm H1 provided by the package dynamic systems returned a value that it's not exactly the same as the one in the returned by the proposition or by the proposed method, with a little error to the order of 10 to the minus 6. Moreover, we tried more than one random matrix to study more this numerical function norm H1, and we noticed that for many equations or for many matrices, and for example for this one, the norm H1 applied to this function returned an error. Okay, it didn't even function. So we continue now to comparing the behavior of the three algorithms that we proposed. So we, through a series of computation experiments in Maple, and we considered all the matrices to be square of order 2 and of coefficients bit size 2. But we varied the polynomial degrees from 2 to 9. Okay, so as we can see here, the method of separation is the slowest. It takes the much time in the experimentation. So here the numbers denotes the time spent by each method in Maple. Okay. As for the H1-Früher and the H1-Soures, which means the Ruhr method and the Sturm-Abischt method, we can see that they are, in most cases, have the same speed of execution. Okay, so that explains the fact that we already said that the Sturm-Abischt function or method is adaptive, which we can see here. Sometimes the Suarez is of the equal speed of the Ruhr method, and even sometimes it's fasted. So this fact depends really on the example that has been took while executing our functions. So finally, for doing our conclusion, we consider three symbolic numeric algorithms for the computation of the L-infinity norm of a matrix valued function G. The first one is the Ruhr method, which consists of separating form, then a Ruhr decomposition, and finally isolating boxes for the solutions, and its complexity is in the 6 plus the 5 tau. Then the root separation method consists of separating form, then isolating interval, and its complexity is in D9 tau. And finally, the Sturm-Abischt method, which does D-sign evaluations over either rational numbers or algebraic numbers. And in this way, we obtain either the complexity D6 tau or the complexity D7 plus D6 tau. As for the further work, we aim to apply the same study over rational polynomial functions or over matrix valued functions that depends on parameters. And thank you so much for your attention.